I have a question for you. What if you use a giant battery to power your tiny watch? What happens if you use a 12 volts power supply on a device rated for 6 volts? Will it only draw the power that it needs, or will it overheat and explode? The key to answering all of these questions is understanding electricity. To understand electricity, let me introduce you to some fundamentals and terminology, like current. Current is the amount of electrons that flow through a wire per second. It's expressed in amperage or amps, or just the letter A. Just like electrons flow through a wire, water will flow through a garden hose. In the garden hose, the current is the amount of water that flows per second.
Yep.
But why does the water flow? Let me introduce you to the concept of voltage. Voltage in a circuit is like a force that pushes electrons. Higher voltage will push current towards lower voltage. In our garden hose example, the pressure from a water tank will push water out of the faucet through the hose. Let's talk about power. You may have heard of power in the horsepower of a car. In an electrical circuit, we measure power in watts. To increase the power in a car, you increase the size of the engine. To increase the power in a circuit, you increase the voltage or the current. They're multiplied to get power, so if you have a low current, high voltage circuit, you get around the same power as a high current, low voltage circuit. Let's think about our garden hose. We're going to get around the same flow from a small nozzle and an opened up faucet as with a large nozzle and a closed off faucet.
Action.
Another way to think about power is energy over time. So let's think about energy in terms of circuits. So if power is energy over time, and we have some power for some time, and we can integrate that, and we get energy. Energy can intuitively be stored in a battery, or it can be used in a circuit. As the electrons move through these wires, some of their energy is dissipated as heat. Let's take the fundamentals of voltage, current, and power and apply them to the questions I proposed earlier. For the big battery on the small watch, do we get a fireworks show when we connect the wires? You might think that the battery sends too much power, but this doesn't occur because there's a component in the watch called a resistor that limits the amount of current, which in turn limits the power. The watch fails for a different reason, related to my second question. The battery voltage exceeds the limit of the watch, which breaks the device. This is understood by thinking about the water pressure analogy. The paper acts like a resistor and blocks the high water current. However, a high-pressure water stream pierces quickly through the paper, just like excess voltage across a resistor breaks it and stops it from resisting current flow, allowing excess power and dissipating excess heat. Intuitively, too much heat can damage electronics. So let's take a look at how that happens. Heat can change material properties, usually making a material softer or more fluid. This causes it to be able to be warped or causes it to warp itself. In a circuit, if a material heats up and warps, it may cause unwanted connections and cause sparks. or break necessary connections and disable the circuit's function. So, since heat causes sparks, fire, and broken circuits, how do we prevent it? For one, we limit the voltage below all the component voltage limits. As long as that's true, there's a general rule of thumb I want you to remember. Current generally generates more heat than voltage. And burn it into your mind, because I can't give you an explanation, it's a little beyond the scope of this video. Current generally generates more heat than voltage. Now, with all the theory I've shown you, you'll learn how these ideas apply to electrical safety in the real world.
So the power that the laptop needs to run is 19 volts. And so the power needs must be met by the power coming into the laptop. The current outlet voltage is 122 volts. It's usually around 120. And the transformer will take the 120 volt input and reduce it down to 19 volts. That's the specified rating for this transformer. So the power going into the laptop will be 19 volts, which is what it requires. So the voltage requirements of the laptop being at 19 volts, if you were to supply the power at too low a voltage, say 10 volts, then the laptop components wouldn't operate because they require the 19 volts to operate. And if you were to have the voltage too high, say 30 volts or 50 volts or even 120 volts, you would probably fry most of the components in the system because they're designed to run on only 19 volts. So we have a 12 volt charger, and the red is always going to be positive and the black is always negative in a 12 volt system. It's very important that you never touch the connectors together because it will short the battery. On the note of battery destruction, always use a compatible battery charger. Battery charging rates and voltages can vary between batteries and battery types. Use of incompatible chargers can lead to overheating, fires, and battery damage. For ENES 100 students, this means you're not allowed to use lithium-ion batteries. Remember to always store your batteries safely, for example, in a battery storage pouch. If your goal is to have a certain power output, it's better to have a higher voltage and a lower current. This is because higher currents can develop a lot of heat, and so it's better to increase the voltage. But remember, it's important not to overpower or have too high of a voltage for your device's needs, because that can damage it. If the power output is not held constant, then increasing the voltage will increase the current. This is due to Ohm's law. Because the resistance is the same, you'll generate more heat in the system. So the current draw is regulated by the power needs of the device. Up here we have an LED light, and it's currently only drawing 0.07 amps. So the current is 0.07. Here we have a much higher, brighter halogen light, and when we plug that in, we see that we're now drawing 4.37 amps total. So it'd be 4.3 amps going to this one, which is 62 times more power than that's required by the LED light. For some devices, such as an old incandescent light bulb, it has elements that resist the current flow. The current the device will draw is determined by Ohm's law. Because voltage is defined by the plug at the outlet, and resistance is defined by the light bulb. Many modern electronic devices will vary the amount of current needed based on the power needed at that moment. A good example would be an electric car going up a hill will require more current. Wire connections must be rated for the amperage being drawn. You must be careful if a device will draw more current than the wires will allow. If you plug in too many appliances to a 15 amp circuit, for instance, and they're going to draw 20 amps to run, then you must have some system to protect the wires, otherwise they'll overheat. Typically this is done by circuit breakers, which will only allow a certain amount of current to flow through the wires before they trip. That will save the wires from overheating and causing potential fires.
Crap.